Hey everyone, and welcome back to The Explainer. Today, we're taking a sort of architectural tour into the microscopic machinery that literally builds the physical world around us. Just imagine for a second that you're a master architect, right? But instead of steel beams and concrete, your building blocks are individual atoms. We are going to explore a single, perfectly engineered structural feature that acts as the absolute cornerstone of synthetic organic chemistry. I'm talking about the carbon-oxygen double bond. Okay, so let's start with something you've probably already experienced today. Think about that rich scent of vanilla beans, or maybe the comforting warmth of cinnamon. The molecules responsible for those experiences, vanillin and cinnamaldehyde, they actually share a fundamental feature. It's a carbon atom double bonded to an oxygen atom. That right there is the carbonyl group. It's the microscopic engine driving these everyday scents, and as we're about to see, it's literally the building block for fabrics, flavorings, plastics, and even life-saving drugs. So here is our roadmap for today's explainer. We'll meet the carbonyl engine, compare aldehydes and ketones, look at the nucleophilic attack, see how we build bigger carbon chains, explore the carboxylic acid shield, and finish up with the blueprint of modern industry. All right, part 1. Meet the carbonyl engine, our polarized foundation. Now, what's really fascinating here is how oxygen's high electronegativity completely dominates the space. Oxygen basically acts like a molecular vacuum, pulling the electron density right toward itself. This creates a highly polarized, completely flat target with exact 120-degree bond angles. So the oxygen becomes this negatively charged magnet, a nucleophile, while the carbon is left totally exposed as a positively charged electrophilic target. This one specific structural quirk, it dictates absolutely every physical property and chemical reaction we are about to talk about. To put that into perspective, this polarized engine places carbonyls right smack in the middle of the thermodynamic ladder. At the bottom, you've got a basic hydrocarbon like N-butane, boiling around 273 Kelvin because it only has really weak van der Waals forces. At the very top, an alcohol like propan-1-ol boils at 370 Kelvin thanks to strong hydrogen bonding. But right in the middle, around 322 Kelvin, we find our carbonyl compounds, like propanol and acetone. They don't have the heavy hydrogen bonding of alcohols, but that polarized engine creates dipole-dipole interactions, which makes them significantly stickier than your basic hydrocarbons. Moving on to part 2, aldehydes versus ketones, the variations in the blueprint. Before we get into how they behave, their history is actually hidden right there in their common names. Formaldehyde, for instance, comes from formica, which is literally the Latin word for ants. And acetic acid comes from acetum, the Latin word for vinegar. Those names point to where they were originally found in nature. But to keep things organized today, we use the highly systematic IUPAC nomenclature blueprint. You just replace the alkane E with a specific suffix, right? So you get methanol for aldehydes, or ethanoic acid for carboxylic acids. So the absolutely crucial thing to grasp before looking at their structures is understanding their core personalities. Aldehydes have very low crowding and are highly reactive. They're just completely exposed. Ketones, on the flip side, have high crowding and lower overall reactivity. They are heavily shielded and incredibly stable. If you look at their physical structures, you can see exactly why this happens. An aldehyde has this tiny hydrogen atom attached to the carbonyl carbon. That means there's almost no spatial crowding, or what chemists call sterics. It is basically a wide open green light for a chemical reaction. A ketone, however, is flanked by two bulky alkyl groups. Not only do these big groups physically block the carbon, making it super hard to attack, but they actually donate electron density back into the carbon, which soothes its positive charge and really calms its reactivity down. And you know what's cool? Chemists exploit this exact difference to instantly tell these two siblings apart in the lab, using mild oxidizers. Because aldehydes are so vulnerable and ketones are so stubbornly stable, we can use chemical tests to force a visual reaction. We actually have two famous tests for this. Toland's test uses ammoniacal silver nitrate. If you have an aldehyde, it oxidizes, and the silver ions reduce to coat the inside of the test tube in a literal, stunning silver mirror. And that works for all aldehydes. Then there's Felling's test, which uses copper sulfate and creates this striking reddish-brown precipitate, though that one only works for aliphatic, straight-chain aldehydes. But here's the kicker. Ketones resist this mild oxidation entirely. No mirror, no red precipitate, nothing. Part 3, the nucleophilic attack. Let's stress test the engine. The core reaction here plays out in 3 mechanical beats. First, a negatively charged nucleophile approaches our vulnerable, partially positive carbon. Second, we get the impact right at the electrophilic target. And third, to absorb that new bond, the entire molecule undergoes a massive geometric reconfiguration. I like to call this step the pop. So as the nucleophile comes in, the mechanics are wild. Unlike alkenes that undergo electrophilic addition, our polarized carbonyl engine is basically begging for a nucleophilic attack. Upon impact, the double bond snaps, pushing the electrons up onto the oxygen. The geometry literally pops from a flat 120-degree plane into a three-dimensional sp3 tetrahedral structure. By intentionally weaponizing this target, chemists can engineer some incredible intermediate molecules. For example, using a base catalyst, we can attach hydrogen cyanide to build a cyanohydrin, or we can add sodium bisulfite to create a water-soluble complex that perfectly purifies aldehydes. We can even add alcohols, using dry HCl gas to boost the carbon's electrophilicity to build complex synthetic structures called acetals. We are quite literally snapping on functional groups like Lego bricks. Part 4. Building bigger carbon chains. Welcome to the construction phase. This right here is a stroke of architectural genius from nature. The carbonyl's powerful electron vacuum creates a literal weak spot at the adjacent carbon, known as the alpha carbon. It weakens the alpha hydrogen bonds, making them unexpectedly acidic. If a base comes along and removes that hydrogen, the molecule itself turns into a potent new nucleophile. That new nucleophile can then attack a second carbonyl target. They snap together, a water molecule is eliminated, and boom, we've just linked short chains into a much larger structure. This is called the aldol condensation, and it's an absolute masterclass in building carbon frameworks. But wait, that brings up a really fascinating mystery. This whole chain building process totally relies on that alpha hydrogen weak spot, right? So, how does the blueprint react when that crucial alpha hydrogen just doesn't exist? What happens when the carbonyl is completely isolated? Well, the answer is the Cannizzaro exception. When an aldehyde lacks an alpha hydrogen, like formaldehyde for example, that aldol reaction is mathematically impossible. Instead, if you subject it to concentrated alkali and heat, the molecules undergo this radical disproportionation. They basically undergo self-oxidation and reduction at the exact same time. It's an elegant molecular trade-off where it literally sacrifices one molecule, oxidizing it into an acid, just to elevate and reduce the other one into an alcohol. Part 5. The carboxylic acid shield. Let's see how the system stabilizes itself. In carboxylic acids, we still have our central carbonyl engine, but it's got a hydroxyl group right next door. And this group acts like an electronic shield. It donates electron density right back into the carbon, stabilizing the whole system through resonance. This massively lowers its vulnerability to attack. But at the same time, it turns the molecule into the ultimate acid, because the resulting carboxylate anion is perfectly and symmetrically stabilized by that same resonance. Carboxylic acids are more than happy to shut a proton, making them way more acidic than simple alcohols or phenols. And finally, Part 6, the blueprint of modern industry, the finished world. Stepping back, we can see the entire convergent synthesis map. Chemists have figured out how to funnel a vast array of materials by oxidizing alcohols over silver and copper, or performing ozonolysis on alkenes with zinc dust, or reducing nitriles, all toward this single carbonyl engine. Why go through all that trouble? Because mastering this specific architecture unlocks our modern reality. We use it to create formalin for bakelite plastics. We use acetic acid for vinyls. We manufacture millions of tons of acetone for heavy industrial solvents. We even use it to synthesize adipic acid, which is the literal backbone of the nylon in the clothes you might be wearing right now. It all traces back to oxygen's electronegativity and a flat, polarized carbon target. When you really stop to consider the carbonyl's invisible presence in absolutely everything, from the scent of your morning coffee to life-saving pharmaceuticals to synthetic fabrics, it leaves you with one major question. How will mastering this single, microscopic chemical bond continue to engineer our future? So next time you smell vanilla, maybe take a second to appreciate the polarized engine making it possible. Thanks for joining me on this architectural tour here on The Explainer. Keep wondering, keep learning, and I'll catch you next time.